Hello everyone, it's the Chemistry Kid, and today we're going to be talking about something a bit different. Instead of chemistry, this is actually one of my favorite logic problems that has actually been proven to be quite controversial in the past. It's a classic logic problem that is related to probability, and it's called the Monty Hall Problem. So let me walk you through it. Now, the main thing to keep in mind with this problem is that you are on the game show. You do not know what is behind the doors. On the other hand, Monty Hall is the game show host, so he knows everything. He knows what exactly is behind each of the doors, where the car is, and where the goats are. So be sure to keep that in mind as we're going over the problem. So Monty Hall was a game show host, and on his game show set, he had three doors, number 1, 2, and 3. Behind one of these doors is a beautiful, beautiful red car, and behind the remaining 2 doors is a goat, or something that you just don't really want or don't really care for. Now he asks you, I want you to pick one door that you think that the car is behind. So let's say we pick door number 1. In other words, we're banking on that the car is going to be behind door number 1. And we're also saying that we think that the goats are behind door number 2 and door number 3. Next, Monty says, you know what? I'm going to reveal one of the doors that has a goat behind it. I'm going to tell you which one of the doors, I'm going to tell you one of the doors that does have a goat behind it. I'm going to tell you that behind door number 2, there is a goat behind it. So that's the little goat there. In other words, he just essentially eliminated one of the doors for us, in this case, door number 2. So now we have 2 doors. We have door number 1, which we've picked, and door number 3 left. Behind one of these doors is the car, and behind the other one of these doors is the goat. Now he asks, do you want to switch your original choice of door number 1 to door number 3? Or do you want to stay on door number 1? Now, the question is there a strategy behind this? Is there a better odds of having the car behind your door if you switch? Or is the odds better if you stay with door number 1? Or does it matter at all? Now that is the question. Now what I'm going to do, I'm just going to erase our little goat behind door number 2, and we're going to go over the logic behind this question. So once you've picked door number 1, you're saying that the car is behind door number 1. Right now, we have a 1 in 3 chance that the car is behind the door that we've picked. We have a 1 in 3 chance that the car is behind door number 1. And there's a 2 out of 3 chance that the car is behind one of the other 2 remaining doors. Then the next part of the question is that Monty Hall essentially eliminates one of the doors. In this case, we'll just say door number 2. So he says there's a goat behind door number 2. He tells us that. So we've eliminated, we don't want to pick door number 2. We can't pick door number 2 because he just told us that there's a goat behind door number 2. There's not the car behind door number 2. So since number 2, the option is eliminated, this odds of 2 out of 3, this odds actually completely moves to door number 3. So now door number 3 would actually have a 2 out of 3 chance that the car would be behind it. So this brings us to our answer. We would absolutely want to switch from door number 1 to door number 3, because door number 3 has an odds of the car being behind it of 2 out of 3. In other words, if we were to perform this experiment many, many, many times, it will end up being that the car will be behind the other door, so in this case, door number 3, about 66% of the time, while the car will only be behind our original pick of about 33% of the time. So yes, the answer to this controversial problem is that we do want to switch if he gives us the option. We want to switch to the other door, the remaining door, because it's a higher probability that the car will be behind it. Now, to illustrate this question or this problem, why don't we go over a more intuitive example? So these are 100 jars, and we can't see into the jars. So 100 jars, 99 of the jars have fool's gold, and one jar has real gold. So we obviously want to pick the jar with the real gold in it. Now, let's say I were to give you the opportunity to pick one jar. We only have a 1 in 100 chance that that one jar will have the gold in it. So let's say we want to pick this jar right over here. So we're banking on that this jar circled in blue will have real gold in it. So right now that jar circled in blue has a 1 in 100 chance that there's gold in it, while the odds of the gold being in any of the other jars is 99 out of 100 chance. Now, what if I say I'm going to eliminate 98 of the jars for you? So we're going to eliminate 20, 40, and we'll just eliminate that one there, 60, 80. So we've eliminated 98 of the jars. So right now we have 2 jars left. We have this jar that we originally picked and this one jar remaining. So this jar that we originally picked, it still has a 1 in 100 chance of having gold. But now this jar actually takes that 99 out of 100 odds into itself. So this jar has a 99 out of 100 chance that it has gold in it. So in this case, we've eliminated 98 jars and we're left with 2 jars left. And by an overwhelming amount, we would want to switch to the other jar if given the opportunity, because the odds of the other jar having the gold in it is 99 out of 100 chance. So this problem is similar to the Monty Hall problem, and it just illustrates the fact that if given the opportunity, you would want to switch to the other option because it has significantly better odds that the either the gold or the car, however you want to think of it, will be behind the remaining option. Now be sure to subscribe to my channel, and also don't forget to discuss in the comment section any questions that you might have, because someone else may have a really good explanation that makes more sense to you.